Hello and welcome to 15 years of AWS Silicon Innovation. My name is Ali Saidi. I'm a Senior Principal Engineer in AWS, and I'm also the Lead Engineer for our Graviton2-based instances. Today, we're going to talk about why we're investing in building custom chips in AWS. And really, it's about our customers. Building our own chips lets us innovate on behalf of you faster, raise the bar in security, and deliver more value. The three areas we've invested in our own chips are the AWS Nitro System. These Nitro Cards are the accelerators for I/O, raise the bar in security, and allowed us to simplify components in our system. AWS Graviton, which are processors for host compute that enable the best price performance in a wide variety of workloads in EC2, and our machine learning chips, AWS Inferentia and AWS Trainium, which cut the cost of inference and training using ML in your applications. I'm going to talk about each of these now in turn. AWS is the only cloud provider that has built chips that span the breadth of I/O, accelerators, and compute. Why do we do it? Well, we believe it will improve our customers' experience by delivering higher performing, more efficient solutions. Building our own chips gives us better time to market, raises the bar in security, and improves reliability. We get to build things from the ground up. And so we get to build the chips for our use cases, which means we get to focus on the features that are necessary for our customers, and we don't spend time or resources on the things that we're not going to use. Developing our own chips also means that we control the development process from when we start the project to when we deliver it. And we can have a repeating cadence of improvements and progress. It also lets us bring products to market sooner. Our hardware and our software teams work together from day one to build the best solution. And when you have the team developing the silicon, the software, the hypervisor, the I/O devices, all under one roof, there's faster innovation, there's easier time debugging, and there's cross-cutting quality. The last is operationally. We get to bake into features into our designs that allow us to do things like live update the firmware while the system's running, without disrupting the customer experience. Let's take a minute now to look at the more traditional compute environment, and then we'll see how silicon we've built at AWS has changed that. So this is a block diagram of a typical server. At the heart of it is a processor, typically from Intel or from AMD. The processor needs some storage, and here I'm showing some NVMe attached to it. It needs networking, and I'm showing a network card. And perhaps it has an accelerator or a GPU, which I'm showing here. At AWS, we're innovating across all the devices you see here to raise the bar in security, enable higher performance, higher availability, and provide you with more value. The traditional I/O card I showed on the previous slide, we've replaced with our Nitro cards. These provide higher performance I/O than would otherwise be possible. The Nitro also lets us raise the bar in security. We have the Nitro security chip, which allows us to protect critical motherboard resources. We also have Nitro cards that enable local storage and allow us to encrypt that storage with an ephemeral key that's destroyed when your instance is terminated. AWS Inferentia and the upcoming Trainium is custom silicon that allows us to accelerate machine learning inference and lower the cost of you using machine learning in your applications. And finally, well, from the beginning of EC2, we've had Intel processors and more recently AMD ones. We've also started building our own. We're on our second generation now of Graviton processor, and Graviton 2 provides up to 40% better price performance, increased efficiency, and reduced power consumption. Let's start by diving into AWS Nitro. Nitro is a fundamental rethinking of how virtualization is done, and the first place that we invested in custom silicon. It lets us provide higher performance to our customers, it raised the bar in security, and it allows us to rapidly deliver new and varying instance types. So if we back up, we launched Nitro back in 2017 with the C5 instance. But Nitro's actually been in development since 2013, when we added the first bits of custom hardware and software to our servers and moved some functionality particularly networking, off of the host CPU and onto that special purpose hardware and software. This ultimately let us simplify the hypervisor, and we replaced the Xen hypervisor we've been using for a long time with our own based on Linux and KVM. Since 2017, all new EC2 instances that we've launched have been based on the Nitro system. So whether you used a C5, M5, or R5, one of our AMD-based instances, or one of our Graviton-based instances, you've been using the Nitro system. There's a reason we call Nitro a system, and that's really because it's composed of 3 independent but very important parts. As I mentioned, prior to Nitro, we used Xen. Xen's great, but it also did a lot. It did device emulation, it did logging, it did monitoring. It's got a full-blown Linux user space. And all of this uses resources on the CPU. So we were looking for how can we simplify that. As we've started moving functionality off of the host, we ended up being left with a simple hypervisor that just did memory and resource partitioning. No real Linux user space, no BusyBox, no systemd. So where did all that functionality go? Security is the most important thing we do in AWS. And since it's such a priority for us, it's also the first thing we think about when we start building something. When we decided to build Nitro, we tried to determine, what is there more we could do from a security point of view? And that led to the development of the Nitro security chip. This purpose-built security chip takes security functions away from a vulnerable place, the host CPU, and runs them on a dedicated resource that reduces the attack surface and mitigates against many threats, and also provides a root of trust in hardware. So I mentioned that the I/O moved off of the host. Where did it go? Well, it went to the Nitro cards. There are I/O accelerators in the system. Not necessarily a single card, but we've got Nitro cards that enable enhanced networking, enhanced EBS, and let us drive to higher levels of performance than was possible with a hypervisor-based solution, while keeping all the resources on that host available for our customers. We also have a passive endpoint that provides all operations on our Nitro hosts. I'm just going to have time to dive into one of the particular cards. I'm going to talk about the Nitro card for VPC. This is the hardware device that interacts with the ENA device driver you might have in your instances. It's also the first thing we use Nitro for. Over time, we've gone from 10 gigabits a second to 25 gigabits and to 100 gigabits. And through that, normally, as you increase the speed of your network, you have to change the driver. But when we started and built ENA, we wanted to be independent of speed. So customers wouldn't have to make a change, wouldn't have to change their driver to get higher performance. Today, we've got drivers available for all major operating systems, and both for x86 and for ARM. The card itself offloads functionality including packet encapsulation, enforcing security groups, limiters, routing. This is all done on the card to be as close to the server and as low latency as possible. By moving this functionality out of a hypervisor and onto a special purpose hardware, it's also let us have bare metal servers that have the same feel as our virtualized instances, including our macOS instance. And we've extended this functionality further with our Elastic Fabric adapter for HPC, MPI, and ML workloads. So I'd like to spend a few minutes talking about the Nitro hypervisor and how we've reduced jitter by using it. Here I'm showing the wake-up delay after an instance says it wants to run something. How long does it take for that to actually run as a probability density function? And so I'm going to start with Xen. Our C4 instance was the last one based on Xen, and you can see here that it took between 75 or 70 microseconds and 170 microseconds for the instance. And we were pretty proud of this, but with Nitro we thought we could do better. And you can see, in fact, that we did. The distribution in the C5 instance, which is our first Nitro instance, is shrunk and has moved way over to the left. And now it's hovering around 25 microseconds. With Graviton and our C6Gs, we thought we could do even better. And here too we did. The distribution is moved even further to the left and even tighter. And we continue to focus on this. Nitro hasn't only had a major impact on security and performance, but it's allowed us to accelerate our pace of innovation. It took 11 years for us to go from one EC2 instance to 70 instances. But in 2017, there was a change, which corresponds to when we introduced Nitro. Nitro's allowed us to create new instance types much faster than we had before. And in just 3 years, we've gone from 70 instances to around 400. This rapid innovation means greater choice of compute, networking, storage, so we can better tailor the resources of the cloud to your workload and optimize performance and costs. Next, I'm going to talk a bit about Graviton. A general purpose processor is the heart of an AWS instance. And AWS Graviton are purpose-designed chips for host compute that are available exclusively in AWS. ARM processors are ubiquitous around us. For years, they've powered the phones and tablets that we use every day. And they've also started to show up in laptops, and with Graviton 2, servers. Our Graviton 2 powered processors have targeted optimizations to reduce power consumption, which means they're less expensive to operate, and we get to pass that savings on to you. We're in our second generation of Graviton processor now. We announced the first one back in 2018, and a year later, the second in 2019. The second generation increased the core count by 4x, the performance by 7x, and the performance per vCPU by almost 2x. These are absolutely huge numbers. Today, Graviton instances are available in 9 instance types in nearly all of our regions. And they use the Nitro building blocks that I just spoke about. We designed Graviton 2 to provide the best value for our customers. It's powered by an ARM Neoverse N1 cores, and we work closely with ARM on that core. It's a large chip. You can see a picture of it here in the right-hand corner, but it's got 30 billion transistors, and it was the first 7nm silicon we had inside AWS. The end-to-end ownership and the design and development of Graviton meant that we only had to build the functionality we needed. We could test that functionality really early in the design process, and we could deliver that functionality in a fraction of time of the incumbents. We built Graviton 2 to have consistent performance across all its CPUs. And for a given performance, the processor is around 3 times more power efficient than their x86 counterparts. That means it's greener, less expensive to run, and you can see that reflected in the costs. So now I'm going to talk some about the functionality that makes the Graviton 2 perform. But to do that, I've got to start with how a lot of our x86 processors work. There's a processor core. This is what fetches and decodes instructions. For example, if you have an add instruction, that's where it gets executed. To make the processor fast, there are caches. There's an L1 instruction cache that maybe holds an instruction that says add these 2 numbers together, and a data cache that maybe holds the data for that add instruction. And you can access those L1 caches in a couple of cycles. There's an L2 cache, which you typically access in around 10 cycles, and beyond that, L3s in tens of nanoseconds and memory in hundreds. Over time, these cores have gotten pretty big, and to improve efficiency and performance, both Intel and AMD have had multiple threads. When I say threads here, I don't mean OS-level threads. I mean what Intel refers to as hyperthreading, or others call simultaneous multithreading. Each of these looks like a separate CPU to the operating system, but really they're sharing resources in this core. Now, the upside to that is, yes, the threads do improve performance, but the downside is they contend for resources in that core and caches. For example, maybe there's only one divider. So if a thread wants to divide, if both threads want to divide rather, one thread has to wait. With Graviton, every vCPU is its own core. There aren't any hardware level threads. Each CPU is smaller and more efficient, so we can put more of them on a chip. And they provide better scalability, as the L1 and L2 caches and the core aren't shared. There's a whole class of security issues we've seen over the last few years that don't apply because Graviton isn't multi-threaded. Beyond that, the core in Graviton has been optimized for server workloads. As I mentioned, ARM's hugely popular in tablets and cell phones, but these aren't a server. while a modern web browser and a Node.js application look similar in a lot of ways, the server is doing orders of magnitude more context switches, system calls, and running more VMs. And we push the latency of all these operations lower. Because there's no threads, we also have a lot more cache for every vCPU. That's 4x more cache in the L1s and twice as much cache in the L2s. So we've got these cores. They don't have threads, they've got big caches, they've been optimized to server workloads. Now we have to put more than one of them together. If I could lift the lid off the picture I showed you a few slides ago of the Graviton processor, you'd see something that looked like this. The black square in the middle, that's the piece of silicon that contains all 30 billion transistors. In there, we put 64 cores and connected them together with a 2 terabyte a second mesh. They're all close together on the same piece of silicon. So if you have cores working on a shared problem, we want them to be able to communicate with each other quickly. Along with that, there's a 32 megabyte last level cache. And if you add the last level cache and all the per core caches together, you get nearly 100 megabytes of user accessible caches on the chip. I mentioned we have 9 instance types already, and there's a 10th one coming. And this is enabled by all the flexibility we have with different PCIe configurations. And we've got 8 channels of DDR4 3200. This provides up to 200 gigabytes a second of theoretical memory bandwidth, and it's really easily accessible bandwidth. If you run simple loops on all the cores, you'll get there without any special trickery. One thing you'll notice is missing is there's no multi-socket. Why? We don't actually think most people need it. It leads to NUMA issues and scalability problems. NUMA stands for non-uniform memory access. And it really asks the question of, is the path from cores to memory the same, or is it different? Is there near memory and far memory, or just one? Not that many people know what it is, and even fewer write software to take advantage of NUMA. And they just rely on the OS to handle it. So the OS has really imperfect information. And we get rid of all those problems if we have all the compute on one die and a single socket system. Now, here I've got several examples of benchmarks comparing an AWS Graviton2-based M6G instance to an M5 instance. Now, there's no substitution for running your own workload. And I really recommend that if you are looking at moving to Graviton, to try one of your own workloads and not rely on a benchmark. Because your own workload is the only real indicator of performance. But I have 3 different workloads here to talk about. The first is SpecInt 2017. So this is a collection of CPU-intensive workloads that includes things like compiling code, running Perl, route planning, discrete event simulation, XML to HTML conversion, Sudoku solvers, and others. Here you can see the Graviton 2 powered instance is 44% faster per vCPU than the M5 instance. In a workload similar to what many of you run, I've got Nginx here, which is configured as a load balancer. It can be a web server or a load balancer, and in this case, we've chosen to configure it as a load balancer. So we've got one simulated system running 512 clients, all accessing the load balancer, and the load balancer is balancing between 4 backend servers, all in a cluster placement group, all using HTTPS. And here you can see the Graviton 2 powered instance can deliver 24% more requests per second. And finally, I've got Memcached. Memcached is a popular key value store. It's used to look up data faster than you could query a traditional database and improve application responsiveness. Here we're using small keys and values just to not make the network the bottleneck. And you can see the Graviton 2 powered M6G is able to perform 43% more requests per second compared to the M5. So we've got a great performing CPU, but how much power does it use? In a typical mainstream server, the CPU is the largest consumer of power. So how does Graviton 2 stack up? It's actually the most efficient CPU we have, more so in terms of performance per watt than our Intel or our AMD systems. For example, an R6G.Metal is over 3x higher performance higher performance per watt than an R5 metal. And since we always look to pass on cost savings, what this means for customers is lower cost, because lower power consumption means it's cheaper to operate. It can be built more dense, so it uses less physical space, and it has a lower impact on the environment. Our Graviton2-based instances provide up to 40% better price performance over their x86 counterparts. And we have 9 different types at this point, with a 10th one with GPUs that's on the way. They range from a 1 vCPU medium all the way up to 64 vCPU 16x larges. We've got C's, M's, and R's in our traditional 2, 4, or 8 gigabytes of DRAM for every vCPU, a burstable instance with T4G, where there's a free trial through the end of 2021, X2GD, which has 16 gigabytes of RAM for every vCPU, and the lowest cost RAM in EC2, as well as variants with disks with M6GD, C6GD, and R6GD, C6GN, which has 100 gigabits of networking, and most of these are available in bare metal instances as well. So these are based on the results I just showed you, the highest performing instances in their instance families. They're all priced 20% lower compared to the same or comparable instances. And if you put these together, that drives a 40% better price performance. And as I mentioned, there's a T4G trial going on today through December 31st, where you can get an instance and experiment with it. Now, I'm happy to say this just isn't our data. Customers such as SmugMug, Snap, and Lyft are part of a growing list that have migrated to Graviton and said it was a lot easier to migrate than they thought. So let's look at some of those quotes now. Lyft's obviously a transportation company. They have applications written in Python and Go where they saw 30% better price performance and report moving was relatively straightforward and are looking forward to running the majority of their fleet on C6G instances. Nextroll is a marketing platform and has applications written in Erlang, Go, and Java. And between the improved performance and the lower cost, they realized an amazing 50% cost savings, and said that all their software packages that they needed were there and it was easy to migrate, and they're going to move everything they can to Graviton 2. SmugMug has been a customer on Graviton since the A1 instances, and they have a PHP-based photo serving app where they realized 40% better price performance and said it required minimal changes. They described it migrating to Graviton as easier than upgrading their operating system. And lastly, Snap. Snap uses Elastic Kubernetes Service, EKS, to run its messaging core service on Graviton, and they were able to reduce their fleet size and significantly lower their costs. So, how can you use Graviton? Well, the price performance benefits are tremendous, and there are a number of ways you can take advantage of them. The first is through our managed services. Amazon Aurora, Amazon Elasticache, Amazon Elasticsearch, EMR, and RDS all support Graviton, and in many cases, they're the default. If you just create a new Elasticache instance, unless you change it, it'll be a Graviton. These are also some of the easiest ways to try to use Graviton, as someone else takes care of installing the software on them, and in most cases, you just have an API that looks the same, whether or not it's running on an x86 instance or one of our Graviton-based ones. All the popular Linux distributions support Graviton out of the box, including Amazon Linux 2, Red Hat Enterprise Linux, Ubuntu, and SUSE Enterprise Server, as well as others like CentOS, Debian, Fedora, and FreeBSD and NetBSD as well. And of course, containers are supported through Amazon ECS, Amazon EKS, or directly through Docker and Kubernetes. And it's also possible to build multi-architecture containers that support both x86 and ARM systems within a single container. We want to make it easy for you to get started with Graviton-based instances and take advantage of the price performance benefits I mentioned. So we've launched the Graviton Challenge. It's a guided pathway to help you get started with a 4-day step-by-step plan And if you want to subscribe to a mailing list, daily tips, tricks, access to Graviton experts, and even some credits to help you. You can also take the Graviton Challenge independently by talking about your experience with the hashtag #ITookTheGravitonChallenge, and enter a contest by submitting a 5 to 10 minute video where you can win prizes including a trip to reInvent. You can find out more at the URL here. Lastly, I'd like to share with you an overview of our machine learning chips, including Inferentia and Trainium, which are easy to use, high-performance machine learning, inference, and training chips that enable our customers to improve their application quality with state-of-the-art models at an affordable price. Let's start with Inferentia. While training chips have received a lot of attention, in reality, many orders of magnitude more inference occur. In fact, based on our own internal usage at Amazon, 90% of the operational costs of building and running machine learning comes from inferencing. Effectively, Inferentia is another Nitro Card, but instead of accelerating I/O, it enables high-performing, low-cost machine learning instances in the cloud. Each Inferentia chip can provide up to 128 teraops per second. The vertical integration at AWS allowed us to design Inferentia, and the server would fit in at the same time. So we can put 16 Inferentia chips into a single server that combined deliver over 2 petaops per second. It's more than double the performance of our P3 GPU instances. The chips also implement a large on-chip cache and is able to run models from that cache. And if you combine that with our fast Interconnect technology, it allows us to string multiple Inferentias together and reduce the latency of inference by as much as a half compared to our GPUs, while keeping high throughput at the same time. I've talked a lot about chips and silicon here, but the investment in our compiler, Neuron, for these ML chips is as large of an investment as actually building the chip, and it's critical to unlocking performance for our customers. The chip plus compiler together mean we can drive the effective utilization higher and lead to better price performance. Inferentia is natively supported by popular frameworks such as PyTorch and TensorFlow, and usable directly through in VMs, containers, or through our managed services. Another factor that helps reduce cost in Inferentia is the performance per watt, or efficiency is around 2x better than GPUs, depending on the particular model. As I mentioned, this allowed us to pack twice the number of Inferentia into a single server. It contributes to the inference per dollar, as well as being more sustainable. Here I've got a couple data points from running YOLO v4 on an Inferentia, Inf1 instance, and a G4DN instance. In the graph on the left, you can see that Inf1 enables 1.85x higher throughput at 62% lower cost per image. In the middle graph, I'm showing latencies of inference running on an Inferentia in blue, which you can see is on the lower part of the graph and very stable, and on the G4DN, which you can see jumps around quite a bit and isn't as predictable, and is also substantially higher. So let's talk about some of the customers that are actually using it. Simple ML models can run on CPUs, but as ML science improves, the models grow in size and make it prohibitive for customers to adopt them. Also, the large model means there's more compute, which can be a real problem for real-time applications like voice assistants or search, where latency is particularly important. Inferentia is compelling for these customers to run into these types of issues, massive amounts of inference and tight latency budgets. We see customers like Snap running recommendation engines, companies that deal with massive amounts of text like Condé Nast and Anthem, as well as applications that need high-performance computer vision like Skywatch for satellite imagery and DMP for driver safety. We're also very proud that customers within the Amazon family have adopted Inferentia and Inf1 in a big way, like Amazon Advertising, robotics, recognition, and of course, Alexa. I'm sure you've seen an Alexa before, and when you speak to an Alexa device, Alexa's text-to-speech service is used to synthesize the response. Last year, Alexa announced they're moving to Inf1, and they've already migrated the majority of their voice traffic to that instance type. If you ask Alexa a question today in English, British English, German, or Japanese, Alexa will be speaking to you on top of an Inf1 instance. Alexa supports over 100 million devices globally, and moving to Inf1 allowed them to reduce their operating costs by around 30% versus GPU instances, while achieving 25% better latency. Now, I've talked a lot about inference. We also have a training chip. AWS Trainium is the first AWS designed chip that we're building specifically to provide cost-effective machine learning training in the cloud. Trainium-based instances will offer the most compute power of any of our instance types, and we'll use the same Neuron SDK as Inferentia instances for machine learning inference. So if you're using Inferentia, it'll be easy to adopt Trainium and get started quickly. Like Inferentia, Trainium will support major frameworks and be available directly through EC2 instances or through our managed services like SageMaker. So I'm just going to wrap up. Thank you for taking the time with me today as we walk through AWS' journey building custom chips and silicon for EC2. Today was a brief overview highlighting some of the innovations in silicon that we've developed, but it's still the early part of the journey, and we continue to look forward to continuing that with you. I look forward to meeting you again in the future to talk about more of our progress here in building chips in order to improve performance, security, reliability, and ultimately allow you to spend more of your time innovating. Thank you.